Greetings students, and welcome to the first of a series of videos for the Physics Advanced students at Francis Parker. Today we'll be starting by talking about the typical forms of units that we use in our scientific endeavors. These units are part of a larger system known as the Système International des Unités, or the SI units. SI, of course, standing for Système International. It's French, which is why it's reversed like that. The system itself is comprised of 7 basic units, but there are really 3 that are of most importance to us, and those 3 are the meter, the kilogram, and the second. These are all units, whereas these are dimensions. We're going to talk a little bit about what's the difference between a unit and a dimension. Maybe you can already guess, but we'll get into that in just a moment here. Alright, so a unit is a standard of measurement. You might, when you typically think of units, think about things like meters, kilograms, seconds, days, whereas a dimension is a measurable quantity, so something that you're measuring. So for instance, meters is a unit, but it measures the dimension of length. Kilograms is a unit, but it measures the dimension of mass. So a unit is a standard of measurement, whereas a dimension is that quality that is being actually measured. So we're going to go through here and just make sure that that's clear. We're going to go ahead and take a look at all of these different units. So these are all units over here, and we're just going to go ahead and talk about what dimensions these units might be measuring. Alright, so before we begin, a little bit of a disclaimer. This is my first time really writing onto this particular program, and I'm going to be using my fingers, so if things look a little lumpy or messy, I apologize, but hopefully it'll still be legible, and hopefully you'll still be able to hear what I'm saying in my words. So, let's go ahead and begin. Meters. Meters, it's a unit, and it measures the dimension of length. So, measures the dimension of length. Feet, another type of unit. It's not an SI unit, but it is a unit, and it also measures the dimension of length. Then there's the kilogram. Kilogram is an SI unit. It measures the dimension of mass. It's important that we not say weight. We're going to talk more in this class later on about how mass and weight are 2 different things. So I wanted to make sure that that's clear. Kilogram for us is in fact a unit of mass, and that is the most correct thing that you can say. Second, again, it's a unit, and it measures the dimension of, hopefully you said, time. And then there's meters per second. So some units are actually derived from multiple other units being combined together. For instance, the meters and seconds, those are both separate units, but we can put them together to create new units. So for instance, meters per second could measure 2 different dimensions. It could measure speed, could be the quality that we're measuring, or possibly velocity. And we're going to talk more about velocity and speed and how they're similar, how they're different later on. Miles per hour, again, you'll notice that we have a length per time, and we have a length per time. So consequently, length per time, length per time. That means that in this case, both of these units are actually measuring the same type of dimension. And so, rather than freaking you out with my terrible handwriting, I'm just going to put those little marks to indicate that this is also a measurement of the dimension of speed or velocity. Joules is a unit. It is the unit for, maybe some of you remember, energy. That's a dimension, something that you can measure. Feet is a unit, and it measures the dimension of, again, length. So we've got a lot of different things we can use to measure length. Of course, in this course, sorry for the pun there, we will primarily be using meters to measure our lengths, as that is our typical SI unit, especially for physics. And then the last one, days, that's a unit, which is measuring the dimension of time. And there you have it. So again, we can see that we have units, and they measure dimensions, measurable qualities of a substance or a thing or whatever it may be that you happen to be working with. Alright, so when we work with the SI system, one of the strengths of the SI system is that it's really easy to modify a unit. We can use prefixes to modify any unit. So in much the same way if you were talking about, a submariner or a subway, right? You can use the prefix sub, which means under, to basically modify what you're talking about. A submariner is someone who travels underneath the ocean, and a subway is a way that is, underneath the streets or underneath the ground. So we can use prefixes to essentially describe, okay, look, this particular unit we're talking about is actually, it's maybe, for instance, if we're talking about a kilometer, right, then maybe we're talking about something that where 1 kilometer is essentially 1,000 meters. Or maybe we're talking about a millimeter, which means that 1 millimeter is 1,000th of a meter. And so these various prefixes can be used to essentially help us describe any unit that we might be working with in the SI system. And because they're essentially all related to powers of 10, it also makes it really easy to convert between all of them. Now, you're actually going to have to know from giga all the way down to nano. Those are the prefixes that you need to know. Don't worry about the nano being highlighted in blue here. That was really just because it was a web link to some interesting stuff about nanobots, but I don't think it's going to work in the video, so sorry about that. Nevertheless, a couple of things to notice. First of all, deca that you can see right here. Deca is one of the few prefixes that is represented by 2 letters as opposed to a single letter. You'll notice all of the other prefixes are symbolized by simply a single letter. Some of them use interesting Greek letters, like for instance, micro uses this fancy-looking M or fancy-looking U, depending on what you want to call it. It's called a mu, MU. That's what it's called, and we use that to represent micro. There are a few other things of note. Actually, before I talk about what's over here, I'll finish talking about the table a little bit more. Besides knowing the prefixes, you're going to want to also know the shorthands for those prefixes, so that if you see something that says MM, you'll be able to understand that, okay, well, the first letter must be milli, the second letter, that's a shorthand for meters, so that must be a millimeter that I'm working with. You're also going to see that I'm going to make extensive use of these times 10 raised to the power of, and you're going to see that if you know those prefixes, you're going to see that you're going to have some advantages when you're doing your dimensional analysis and unit conversions later on. And I would say it's probably more important to know this middle column and this first column than the third column, because essentially if you know the middle column, you should be able to translate that into English. But if you want to go ahead and try and memorize third column as well, you can, but hopefully most of you understand that 10 to the second is the same thing as 100 and 10 to the third is the same thing as 1000. But I'll leave you to decide how you handle this table. But again, during our conversations, if I talk about, for instance, a megagram, I'm going to want you to understand that I'm talking about 10 to the 6 grams, for instance. Okay, so make sure that you know this table. There are a few useful facts and interesting things that you should also consider knowing. First of all, you need to really know one of these two facts. You can either know that a single milliliter is equal to a centimeter cubed, or that a liter is equal to a decimeter cubed. But you really need to know one or the other. These are one of those few things as well that you're just going to have to memorize. You got to choose one or the other. Don't need both, but you need one or the other. And that's because sometimes it will ask you to convert from a volumetric unit, like some type of liter, to a cubic unit like centimeters cubed or decimeters cubed. And as long as you can do one of these two, then you're going to be able to convert from a volumetric unit to a cubic unit successfully. I find that it's useful to know that in 1 hour there's 3,600 seconds. You're welcome to always go ahead and change from an hour to a minute and minutes to seconds, but if you learn this fact, you're going to find that you're just going to save yourself some time in quiz situations, test situations, on homeworks, and so on. And so it's one of those facts I think is worthwhile to try and put to memory. Although it's not technically true, I'm going to say that it's sufficiently true that in this course I'm going to allow us to say that there are 365 days in a year, and that consequently we can indeed use the rent rhyme of having 525,600 minutes. That's okay as well, even though, yes, technically there are a little more than 365 days in a year, which makes this completely false as well. But again, for our purposes, that will be acceptable. So feel free to use those facts to your liking. Alright, so by my estimation, you've probably watched about 20 minutes or so of course material at this point. What I'm going to do now is I'm essentially going to go through and do several different practice problems. Essentially, what I would recommend as I go through these is really taking advantage of that fast forward button. If you see a problem, you're like, man, Mr. Griggs, I know how to do that, I'm not worried about that one, hey look, I did get the right answer at the end, then you're good. I wouldn't worry too much about it. If on the other hand you're not sure what you're doing, you're not getting the answer, then watch through the solving process. So feel free to skip around a little bit in this section. I'm going to start off with some really easy ones, and then it's going to become a little more advanced, a little more advanced, a little more advanced. And I'm going to show you some of the tricks and tips that I make use of as well. The key thing for me, though, is that you're staying organized, you're showing your work, and that you're really showing how those units are changing as you move from the start of the problem to the end of the problem. Essentially what we're doing here is called dimensional analysis, and the idea here is that as long as there's some type of equivalency in the dimension, some type of relationship, we can change from any dimension to any other dimension. As long as we understand that there's some type of equivalency, whether it's because they're both lengths or because a certain amount of length is equivalent to a certain number of counts for some reason or another, whatever it may be, as long as we have some kind of equivalency, we can essentially move from one dimension to another, which can be very powerful in science, where we might be working with something and say, okay, well, I got this and I got that, I got these units, how can I change this into something describing the energy of the situation or whatever else it may be. Okay, so let's do some dimensional analysis, sometimes also referred to more simply as unit conversion, even though there are some nuances that really make a distinction, but we're not going to quibble over those for too long just at this particular moment. Alright, so I'm going to start with this really easy problem. How many feet are there in 17.5 yards? Okay, so remember that there are 3 feet in 1 yard. Now, what we will do first is we will take the given information in the problem, in this case 17.5 yards, and we're going to write that down. It's a whole number in this case, so 17.5 yards. And so consequently, you can really say it's 17.5 over 1 yards. And that's really why I'm putting it up top there, as opposed to on the bottom of that horizontal line. That horizontal line is actually a line representing division, just like if I had 2 over 4, right? that would be 2 divided by 4. And as a shorthand, to represent multiplication, I'm going to use a vertical line. So each of these columns has to have an equivalency. So what I want to do is I want to go from 17.5 yards and change it into feet. So I want to get rid of yards. Since yards is on top, that means that I'm going to need to put yards on bottom in the next column because I want yards to cancel out. I don't want them to be around anymore once I've progressed forward in the problem. And in this case, I want those yards to change into feet. And lucky for me, there's actually a direct relationship between yards and feet. So really this problem is as simple as saying, okay, well, we have our given information, 17.5 yards, and we're going to try and change it to feet. And what we see here is that for every 1 yard, there are 3 feet. Something that's interesting and important to note is that I really focus on the units prior to focusing on any of the math. You can see that I haven't done actually any of the solving yet, and in fact, I'm going to have to go to my calculator in just a moment and punch in those numbers, or maybe do them in my head or whatever, to figure out what the answer is. And so in just a moment though, we will have our answer in feet, and we can see that because the yards have essentially negated themselves. They have canceled out from the top and the bottom, and we are now left with an answer that is only in feet. Alright, so we're going to go ahead and try that out and see what our final answer is. Alright, so it would seem that 52.5 feet is the answer. So again, it's 52.5 feet. Let's always make sure to write units on our answers, and just going to circle it to be all fantastic. Okay, on to the next problem. Alright, so a bunch of you can probably do this problem without even writing anything down. How many millimeters are there in 5 meters? And you're thinking, oh, millimeters, okay, well, millimeter is 1,000th of a meter, so I'll move the decimal places over, I'll do that King Henry, etc. kind of thing, or whatever. Okay, so sure, maybe that's one way you could do it. I'm going to show you another way of doing it, and this is especially good if you understand what all those prefixes that you're supposed to know mean. So I'm going to do it a way that's a little bit long, but I'm going to do it for this simple problem so that you can see how it's useful on longer problems and more complicated problems later on. So let's go ahead and give it a shot. Alright, so again we're going to start with what we have been given. We've been given 5 meters, so 5 meters. And I want to convert these 5 meters, again 5 meters is essentially 5/1 meters. I want to convert these meters to millimeters, so I want to get rid of meters. Notice again I'm focusing on the units first. And I want to change it to millimeters. These are both units of length. It's 2 different units, but they're both measuring the same type of dimension, and in fact I understand that there's a nice easy relationship between these 2 units. And so this is what I'm going to write, and I'm going to explain what I'm going to write, because probably what many of you are thinking about writing first is probably something that looks more like this. You're probably thinking, I'm going to write that there are 1,000 millimeters in 1 meter. And I would tell you, yeah, you know what? That is absolutely true. There's nothing wrong with that. You totally solve the problem from here, and you would get the right answer, and everything would be good. So, bravo, well done. However, I'm going to show you a different way, and I'm going to explain why I do it that different way. So, what I'm going to do actually is, rather than writing it like that, I'm going to say that I'm going to go ahead and just say, for every 1 millimeter, there is 10 raised to the power of meters. Now in this case, milli means 10 to the negative third. If you look back on that table that I talked about earlier, you can see that milli means 10 to the negative third. In other words, what I'm doing right now is I'm taking advantage of what I know about the prefixes. You see, there's an advantage to doing this. One of the classic mistakes to make during these types of problems is to always be asking yourself, okay, well, which of these is the smaller unit? Which is the larger unit? Should it be that there's 10 of these into one of those, or 1,000 of those into one of those, or is it 10,000 of those into one of those? What's the relationship? And I can't tell you how many times I've seen, people say that there's 1,000 kilometers in a meter. And we know that's not true. There's 1,000 meters in 1 kilometer, but they switched them accidentally. And it was because, they were in a rush, or they just weren't thinking, or, they just made an error. Now, what I'm going to do instead is, by the method that I'm using, what I'm going to do is I'm always going to write 1 in front of the prefix unit. So you see there, that's my prefix unit. My prefix unit is millimeters, and I'm going to write 1 in front of that unit. And then I'm going to look at the other unit, which will never have a prefix on it. In other words, I'm never going to go from a prefix to a prefix. I'm never going to go from millimeters to centimeters or millimeters to hectometers, for instance. I'm only going to go from millimeters to meters or hectometers to meters. And so consequently, what I do is I always write 1 in front of the unit that has the prefix, and I'm always going to write 10 raised to a power in front of the unit that does not have the prefix. And in this case, all I need to do is say, okay, well, let's see, for this one, we've got milli up here, so the prefix in that case is meaning 10 to the negative third. And again, this comes from the idea that when you say milli, what you're really saying is you have 10 to the negative third meters. Okay, that's what the prefix is actually telling you. All right, so enough about that. I urge you to try out that method. If you practice it and use it, I think you're going to find you make less mistakes and it works a lot easier. Again, cancel out your units as you go. The other nice thing about this is because you're working with scientific notation and we are a science class, you can actually then say, okay, well, it looks like my answer is actually 5 times 10 to the third millimeters. And in fact, I don't even need a calculator to do that problem either in any way, although you probably didn't need one regardless. Even so, notice again, too, how the 10 to the negative third can be moved up to the top. Hopefully you remember the rule about if you have a negative exponent in the denominator, it can be moved up to the numerator, right? Okay? If not, then please go back and look at simplifying problems where you have exponents that are negative or positive in the numerator and denominator. That's an important thing to understand as far as our math skills go, and it's going to be assumed that you can do those types of problems. So if you can't simplify, for instance, something like this, 10 to the 6 over 10 to the negative third, then you're going to have some problems during this part of the class. And so you should come talk to me early or start talking to your math teacher or whatever, but we need to make sure that you have that skill. All right, excellent. Let's move on to the next problem. All right, for this one I'm going to pick up a little bit of speed, mainly because I want to show you how the power of those prefixes can really make your problems a little bit easier, even with big numbers like this one. So, how many nanograms are there in 5.27 times 10 to the negative 13th kilograms? So we're going to start with what's been given. We've been given 5.27 times 10 to the negative 13 kilograms. Boy, oh boy, I wish I was not writing with my finger. All right, I'm going to change kilograms to nanograms, but I don't want to go from kilograms to nanograms because they both have a prefix. So I'm going to change actually from kilograms to grams. Okay, and again, I always put 1 in front of the prefix, so 1, and 10 raised to the power in front of the non-prefix. So 10 kilo means to the third, so 10 to the third, and now I've canceled out kilograms. Now I'm going to go from grams to nanograms. So grams is what I want to get rid of, so I'm going to write grams on the bottom, nanograms on the top. Notice again that I'm focusing on my units first. 1 always goes with my prefix unit, and I'm going to ask myself, what does nano mean? Because essentially I'm trying to write an equivalency, right? 1 nanogram is the same thing as saying 10 to the negative 9th grams. And again, we can see how my grams cancel out. And so if I start to shift my numbers around, we can see that essentially I have 5.27 times 10 to the, well, let's see, we've got negative 13, so negative 13, we've got 3 up here, and then here's 10 to the negative ninth, but you know what, this 10 to the negative ninth, I'm going to be able to move it to the top so that it's 10 to the ninth. So really we've got negative 13, 3, and positive 9, right? So 9 and 3 is 12, and so really actually we have 10 to the negative 12th, or sorry, 10 to the negative 13th, and 10 to the positive 12, which means that we actually just have times 10 to the negative 1 nanograms, and that's my answer. We'd probably like to see those nanograms. There you go. Alright, so once more we're going to start with what we have been given. We have been given 6.42 times 10 to the negative 4 centimeters. Whoa, centimeters per minute? Yeah, that means 6.42 times 10 to the negative 4th centimeters per 1 minute. Alright, so we can start by trying to get rid of the length and change that into meters, or we can start by trying to get rid of the time and change it into seconds. I'm going to go ahead and start with the length first. There's really no particular reason to do that, it's just what I've decided to do. So I'm going to change from centimeters to meters, and as you've heard me say before, I'm just going to go ahead and write 1 in front of the prefix unit and 10 raised to the power in front of the non-prefix unit. Centi means negative 2. So there we go. Now I am no longer in centimeters per minute, I am now in meters per minute. But I don't want to be in meters per minute, I want to be in meters per second. Because I'm running out of a little bit of space, we're going to actually shift on down to the line below, which means I'm going to do a little solving on the top. Usually I would do all my solving right at the end, but just to make that transition. Alright, so we got 6.42 times 10 to the negative 6 meters over a minute. We're going to change minutes to seconds, so we've got minute, and we've got seconds. And again, the reason this minute was written on the top is because minute was on the bottom over here, and I want to cancel out these two things. So for every 1 minute, there is 60 seconds, and that's going to allow me to cancel out those minutes. And so consequently, I end up with 6.42 times 10 to the negative 6 divided by 60 meters per second. And that gives me this as my answer. Alright, it would seem I've got 1.07 times 10 to the negative 7th meters per second. And again, I get that from taking 6.42 times 10 to the negative 6 meters and dividing it by the 60 seconds. Notice that essentially I'm multiplying what's on the top and multiplying what's on the bottom, and then taking what's on the top and dividing by what's on the bottom, right? Okay, excellent. Let's try another one. How many liters are there in 8 times 10 to the 12th centimeters cubed? So, our given is 8 centimeters cubed, and we're going to change that into liters. Now, one thing we know is that a liter is the same as a decimeter cubed. So for the sake of this problem, even though I admit it's not the only way to do it, but also because I want to show you guys something, we're going to go ahead and try and change centimeters cubed into decimeters cubed. So we can also see that I should probably write the actual number that's been given and not just a made-up number from my head there. So here we go. Though to be fair, the number that is given was also made up from my head. So in any case, we have 8 times 10 to the 12th centimeters cubed, and we're going to change it to decimeters cubed. Now, if you're using my method, then you're probably thinking, okay, well then I need to change from centimeters to meters. And you might even say, okay, well for every 1 centimeter there's 10 to the, let's see, a centi means 10 to the negative second meters, and so I'm just going to say, you know, cube that, and that's the relationship between meters cubed and centimeters cubed. Unfortunately, that would be incorrect. That is simply not true. And the main reason for that is because you're dealing with something that is a cubic unit. It's a length, a width, and a height. It's not just a length. It's not just a width. It's not just a height. It's a length by a width by a height. So what we have to do instead is we have to realize that that relationship of centimeters to meters that the prefix was talking about was for a single dimension. Okay, it was just for length, for instance. So one thing we can do is we can say instead, okay, that really when we say a centimeter cubed, what we're actually talking about is a centimeter times a centimeter times a centimeter. So if we want to get to the point where we've canceled out our centimeters, then we need to essentially do the step that we're looking at here. We need to do it 2 more times. In other words, a total of 3 times. So I'm going to go ahead and do it 2 more times. So we're going to say 10 to the negative second meters is the same as 1 centimeter, and 10 to the negative second meters is the same as a single centimeter. And again, we'll see is that that allows us to cancel out all of our centimeters cubed. And again, thanks to scientific notation, that means that we now have something that is 8 times 10 to the, let's see, we've got -2, -4, -6, but positive 12, so we've got positive 6, so times 10 to the 6 meters cubed. Now that's not the end of it. We want to get to decimeters cubed. However, we can change from meters to decimeters. Now, rather than doing it the way we just did it, I'm going to show us a shortcut. And some of you may already realize what this shortcut would be. What I would tell you is instead focus on what is the one-dimensional relationship. So the one-dimensional relationship is that for every 1 decimeter, there is 10 to the, let's see, deci is -1, 10 to the -1 meters, right? But this is a cubic relationship. So rather than repeating this step twice more so that I have it 3 times total, what I'm just going to do is I'm going to say, well, look, this is the same thing as essentially saying, this is the same thing as saying this times this times this. Well, that's the same thing as cubing, right? That's why they're called cubic units. So what I'm going to go ahead and do is say decimeters cubed, okay, decimeter cubed is a decimeter cubed. 1 cubed, okay, that's 1. A meter cubed, okay, that's a meter cubed. 10 to the -3rd cubed is -3. So 10 to the -1st cubed is -3. Okay. And now we've canceled out our meters cubed, and the last step would be to change from decimeters cubed to our liters. And remember, we know that there's an equivalency between decimeters and liters. For every 1 decimeter cubed, there is 1 liter. And so our decimeters cubed will cancel out, and now we have an answer that's going to come out in liters. And so we see our final answer is, in fact, 8 times 10 to the, well, let's see, we had 10 to the 6, but there's 10 to the -3rd on the bottom, but we can move that 10 to the -3rd on the bottom up to the top, so that we really have times 10 to the 6 times 10 to the 3rd. Right, the 10 to the -3rd is going to be moved up to the top, which gives us essentially 8 times 10 to the 9th, and of course that's now in liters. And so that's how we can do that type of problem. Alright, and that's the last dimensional analysis problem for tonight. See you in class.